Now if we imagine traveling along a curve, in this case we're going from A, let's say, out to B, and the curve looks something like this. Then as we move along, at each x value that we sort of pass through, we've traveled a certain distance along the curve. And that distance that we've traveled along the curve we're going to call s of x. It's going to be a function of x. So this function s of x encodes the arc length of the curve from A out to this other value x. And what we'd like to do is find a formula for s of x. Well, s of x is the arc length along the curve from A to x. So it's the integral from A to x of 1 plus the derivative squared dt in this case. Why did I switch to the variable t? Because x is already being used as a variable of the upper limit of integration. And just keep in mind that the variable used in the integral itself is just a dummy variable. It's going to get integrated away, so it doesn't matter what I call it. We could also write this as the integral from a to x of the square root of 1 plus dy by dt, all squared dt. Now the next part asks us to find the derivative of this arc length function s with respect to x. And so we have an integral representation of our function s, so to differentiate it we use the fundamental theorem of calculus. So this becomes a 1 plus f prime of x squared. To differentiate this integral representation of the function, we just take the upper limit of integration, the x, and pop it into the integrand. We could also write this using Leibniz notation, which is the 1 plus dy by dx all squared. And of course this was by the fundamental theorem of calculus. So one thing to note is that ds as a differential is the square root of 1 plus f prime of x all squared dx, which we could also write as 1 plus dy by dx all squared dx. So just in our two different notations for derivatives. And what we notice is that the differential ds is precisely what appears as the integrand and dx for the integral representing arc length. So we could write the arc length function s as the integral of ds. Right, so all we're doing is taking this stuff here and just noticing that that's what we've called ds. Now it doesn't look like we've done much here, but in some sense what we've done is given ourselves a way to remember how to compute the arc length. If we remember the arc length differential, this is what is called the arc length differential, this ds. If we remember the arc length differential is the square root of 1 plus the derivative squared dx, then the arc length is the integral of that differential. And this arc length differential is going to crop up in other examples where we look at surface areas. So it's going to be sort of the common linking theme between surface areas of solids and arc lengths. So it will be important to remember this arc length differential, and all we're just noting here is that you can remember the arc length formula in terms of that differential. And one other thing to notice is that if we square this arc length differential ds, then that's equal to dx squared plus dy squared. So in other words, we get a relationship between a small change in x, a small change in y, and the resulting change along the length of the curve. And that's not surprising if we look at the diagram, because dx represents this small change in x, dy represents the change in y, and ds then represents the approximate change in the length of the curve. And what we have here is that the length along the curve, the actual change is delta s, and we can estimate that actual change, or approximate that actual change, by the change in the arc length differential. Okay, so let's have a look at the next example. We want to find the arc length function, so we're going to need to know the derivative. So that's 3t to the 1/2. So the arc length function, s of x, is the integral from, well, the starting point is x equals 1, and the ending point, of course, well, our variable x. And this becomes the integral of 1, the square root of 1 plus f prime of t squared dt, which is the integral of 1 to x square root of 1 plus 9t dt. And now we can anti-differentiate, and so there's our arc length function. Now what does this represent? In terms of the picture, we've got a curve that's starting at a point and moving on. Keep going. That's our point P naught. And now as I let x move, I'll get another point x comma f of x. And as x changes, the length along the curve between those 2 points changes. So that's a function of x, and that's what s of x represents. It's the length of this curve between P naught and this other point x f of x. So the length of that red line, depending on x, is given by that function. That's it for this section. Thanks for watching.